Yeah, perfect.
So thank you all for being here. It's our pleasure to welcome Peyman Rostami today, who's going to talk about the influence of complex rheology on drop dynamics. He's a postdoc currently at the Leibniz Institute of Polymer Research. And so Peyman, tell us more about yourself. Where did you study? Bachelor's,
Yeah.
master's, PhD, and what are your plans for the future too?
Yeah. First of all, thank you for inviting me to this talk. My name is Peyman and I'm from Iran. So I did my bachelor and master in Iran and in fluid dynamics. So I was really into this multi-phase flow, like bubbly flows and slug plug flows, doing the experimental and also CFD simulations. Then I guess it was 2019 that I moved to Max Planck Institute for Polymer Research in Mainz. There also I was interested in drop dynamics, drop coalescence, and etc. And then a few months later, I moved to Dresden to do my PhD in Leibniz Institute for Polymer Research. And then now I'm also working on the same topic. So, and also I'm not a very expert rheologist compared to you guys. So I started thinking about the rheology something like less than 2 years ago, that we were interested in these drop dynamics of complex liquids. So that's why when we started to look into the rheology and then this interplay between rheology and wetting. And then for the future plan, we will have a few collaborations running and also a few proposals to be submitted. So I hope to stay in academia, but as you know, it's always tricky to find the right funding and right position and everything. So in general, who knows what would happen.
Okay, yeah.
But it's a pleasure to be here, and thank you again
Thank
for
you. Thank you
inviting
so
me.
much. Of
Thank you.
course. Okay, well then it's time for me to stop sharing and it's time to you to pull up your presentation.
So now hopefully you can see my screen.
Yes.
Yeah, that's
And
perfect.
my laser pointer. Perfect.
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 So hi again, everyone, and welcome to today's talk. Today I will discuss about the influence of complex rheology on drop dynamics. That's a work that we've done in Leibniz Institute for Polymer Research. The talk, I divided the talk into two parts. The first part, which will be something like a 75% of presentation, is about the drop spreading. I will start with the little bit of the background of these experiments, then comparison between the viscous and viscoelastic drop spreading, and then in the last section, I will discuss about the elasticity dominant drop spreading. In the second part, we will discuss about the drop coalescence of, again, complex and viscoelastic liquids, and then there I will point out on the capillary wave and comparison between drop spreading and drop coalescence. So what the first question is that why should we even care about studying the non-Newtonian materials? First of all, because it's present in the nature. For example, almost all the biological flow inside our bodies are non-Newtonian. And also the fundamental knowledge, which will be a key to a wide range of application of these kind of fluids. For example, one of the nice examples that I found is this rod climbing effect. When you have a liquid and then you have a rod inside and start to steering this rod, if it's a Newtonian, it happens what happens every morning that we are stirring our coffees, the liquid is going downward. But for the non-Newtonian cases, due to normal stress differences, the liquid actually climbs up the rod, and that's why it's called rod climbing effect. And then knowing these fundamental knowledges will be a key to understanding the applications like coating, 3D printing, bio and microfluidics. And one of the examples that I personally like for this presentation is the inkjet printing technology. That the inkjet printer deposit the droplets on the substrate, and then these droplets spread over the surface. And then at some points during the time, they coalescence to each other and form this dry film over the surface. The efficiency of this spreading and coalescence will determine the quality of your print. So it's really important for people in inkjet printing that how the ink that they are using interact with the solid substrate or paper or whatever solid substrate that they are using. But if we take a step back and look from outside, it seems that the things are a little bit divided. So most of the fundamental knowledge has been developed for Newtonian cases, but most of the applications are based on non-Newtonian fluids. So in this talk, I'm trying to take a very small step toward addressing this gap between these two branches. And also from another perspective will be that we are combining the wetting and drop dynamic with the polymer physics of material that we have. So if we continue and we remember that the first process in the inkjet printing technology was the spreading of the liquid over the surface, we can make a very simple setup to capture the process of the spreading. So we need a needle to generate the droplet and the droplet hanging on the needle. We need a movable substrate and the stage to bring the substrate slowly and smoothly upward. And then when they collide to each other, the droplets start to spreading over the substrate. And also we need a high-speed camera and illumination system to capture the process. If we do so, we will get a time series of the images like these ones. And then from these images, by taking few steps of image processing, we can calculate and measure, for example, the contact angle, the wetted area radius, and have these data, store them over the time. So as I said, that's a very simple experiment. So it was a subject of a study for several decades. And then I guess that's something like 20 years ago that these high-speed cameras enables us to have better spatial and temporal resolution. This topic getting more attention than before. And one of the nice work, something like 20 years ago, is from David Couret's group in Paris, that they are looking at the drop spreading of water on a glass substrate. When they did so, they find out that the drop spreading is consists of two regimes. The first regime, which they call inertial dominated regime, which the radius of wetted area is a function of a square root of time. And then later follows by a viscous dominated regime, which is known as Tanner's law, which the radius of wetted area is a function of t to the power of 0.1. But for both cases, we can feed the data by a power law with two parameters. One is the prefactor, which we call that B, and one is the exponent, which we call that alpha. And then we will come back to these B and alpha during the talk several times. And in this calc, we are mainly interested in the earliest stage of drop spreading. In the same paper, Professor Curie and his group wanted to present and fit our data with a force balance, and then they came up with a very simple but very nice idea that when you are working with low viscosity drops, the energy should be conserved, and the energy are acting on the drop spreading or consist of kinematic energy, kinetic energy and capillarity. The kinetic energy is a function of contact line velocity square, and capillarity is a function of surface area. By a very simple math steps, you can find out that R will be a function of a square root of time, and the prefactor will carry all the bulk properties like liquid density, surface tension, and drop size. Later, other groups study, like Professor Amberg in Sweden, study the drop spreading of more viscous liquids, and then they find out that when we are adding the viscosity, we are modifying the prefactor. So far, everything seems very straightforward. So we wanted to test this modeling and these models which are existing for Newtonian materials on our viscoelastic materials. So then we need to prepare the samples. We prepared two sets of the samples. First one is the water and glycerine with different concentration of glycerine to have different viscosities. And secondly is the viscoelastic liquid, which is a mixture of water and PO with different concentration of the polymer and also different molar masses, which I will refer to K, which means the kilogram per mole. But there is a point which might be very obvious for this audience, because you are rheologists, probably you know that, but it's not very obvious, for example, for wetting community, that when you are preparing the sample, you should give your sample enough time to polymer to be dissolved in the solvent that you have. For example, it's a flow curve of one of my samples that we prepared, and then after 1 day overnight, I measured the flow profile, and then after 5 days, after 25 days, and 45 days. And then you see that only after 45 days, these polymers reach a steady state situation, and then the sample will not change over the time. But in many papers, I can recall that people said that we prepare the samples overnight and do the experiments on the following days. But when you do so, there is a risk that you have a viscoelastic material doing the experiments, and then the next days, you have a different sample, although you are not seeing the difference between these two samples. So when we are preparing the samples, we should take enough time to reach a equilibrium state of the polymer that we have. So when we have our samples, it's time to test the models by other groups. So we prepare two samples. One is the water and PO 3%, 300 kilogram per mole. And the other one is water and glycerin with 85% of the glycerin. We choose these two, such as the viscosity or the zero shear rate viscosity of both are 100 millipascal second. The initial drop size for both are same. The density and surface tension are almost same, not exactly the same, but from what we learned from the Newtonian materials, they should behave very similarly. And when we let them spread over the surface and then measure the wetted radius versus time for different samples, then we find out very interesting results. The first thing is that for the water and glycerine, we are following a square root of time. So it's Newtonian, and it's also a case, it's a case that we know the results. So when we compare to the viscoelastic materials that we have, there are two differences. One, water and PEO solutions are spreading faster. And two, they are spreading with a different exponent, which is not reported so far in any of these literature that we are discussing about. So we need a systematic study on them. So we did the experiments for different water and glycerine and water and PEO solutions with different concentration and these two molar masses. And then the finding is that for the Newtonian cases, always the exponent is fluctuating around 0.5, so around a square root of the time. So we are consistent in the Newtonian domain. But when we are going to the viscoelastic one, by increasing the zero shear rate viscosity, which means increasing the level of viscoelasticity, which again means increasing the concentration or molar masses, the exponent decreases. And the difference between the Newtonian case and viscoelastic case is getting bigger and bigger by increasing the viscoelasticity of the system. So that was a very interesting observation for us. And then, as you remember, our fit has two parameters. So we wanted to see what will happen for the prefactor. And when we plot the prefactor for both cases, it seems independent of the sample nature. So if we have a Newtonian sample or a viscoelastic sample, the dependency of the prefactor to zero shear rate viscosity is the same. Which again, if we go to the fit that we had, we have a constant prefactor. And in these such low time scales, below 20 milliseconds, a smaller exponent means higher contact line velocity. And that's exactly what we observed beforehand. But these are just observation, and we need explanation. And then to explain that is the point that rheology kicks in. If we look at the flow curve of these two samples that we discussed so far, for the water and glycerine, we have a Newtonian behavior. So by increasing the shear rate, the viscosity remains constant, which we expected from a Newtonian case. And for the water and PEO solution, it's constant, and at the critical shear rate, it starts to thinning. So the viscosity decreases by increasing the shear rate. There are a couple of models to feed these data. One of the nicest one and straightforwardest one is the cross-model fluid model, which is a 4-parameter feed to the flow curve. In that feed, we need 4 inputs. One of them is the zero shear rate viscosity, which is the viscosity at very low shear rates, viscosity at infinity, which we assume will be the viscosity of the solvent, in this case the water, and then it will return the polymer relaxation time scale, which we call the tau. And it's, by the way, it's a rough inverse of the point that the thinning starts. So inverse of the shear that the thinning starts will be roughly equal to polymer relaxation time. And also we have m, which is the rheological exponent, and show the slope of this thinning part. Then how does it help us? It's when we are looking at the dynamic of drop spreading. So when the drop touches the surface, it starts with spreading over the surface with the contact line velocity in order of meter per second. And if we take 1 millimeter or 1 micrometer from the contact point, we will end up with a very high shear rate process. So the process itself is a very high shear rate process. And we know from the hydrodynamic that most of the dissipation happens close to the contact line. So it's the fact number 3 that I want you to recall. And then if now is the time to put all of these pieces together. So if we came back to the force, to the energy balance that we had in the viscous and viscoelastic cases, the energy is not conserved. So the change rate of energy should be balanced with the dissipation. And from the hydrodynamic solutions like Moffat solution, we know that the dissipation, viscous dissipation is a function of viscosity times contact line velocity squared. And then from the other fact that I told you, we are in a high shear rate process, which means the viscosity of the viscoelastic material is way less compared to the viscosity of the Newtonian one. And a smaller viscosity means less dissipation, and less dissipation means higher contact line velocity. So that's a very qualitative explanation that's why a polymer solution in this range should spread faster compared to a Newtonian case. But we wanted to take it to the next step and do quantitative simulation as well. So then we look at the viscoelastic dissipation, and again the same formula by Moffat. But the difference here is that the viscosity is not a constant. So the viscosity is a function in this high shear rate region, is an inverse function of shear rate. And shear rate and the drop spreading is a function of contact line velocity. So in total, the dissipation will be a function of velocity to power of 2 minus m. And then if we put everything together, kinetic energy, capillarity, the combination of these two should be balanced with the dissipation. But if we are looking at this ODE, it's a very ugly nonlinear ODE, and it's very nasty to solve that. And it was beyond the expertise of us to do the full numerical simulation for that. So in collaboration with Dr. Fricke in TU Darmstadt, we came up with the idea to not solve the entire equation set, but solve that as a perturbation to the Newtonian case. So that's why we put this epsilon here, and it's a very first order perturbation to show us that whether we are going in the right direction or not, and not solving the entire data set. So For that, when we are starting from a Newtonian solution, which is given here, then by turning on the viscoelasticity, we are decreasing the exponent. The way that we do that is that we have the analytical solution for the Newtonian case, and then we numerically solve that for first order perturbation of viscoelasticity dissipation in viscoelastic case, and then feed a power load to the data from the numerical simulation. And then by that we see that it decreasing the exponent. But we also look for different cases. For example, this one we are starting around 0.5, which is the water case, and then by increasing the viscoelasticity exponent m, we are decreasing the spreading exponent. But there are two remarks on this slide that I want to make. First, it's just a tip of work, so we don't know what is the full simulation, but we know that we are going in the right direction. And also it's very limited to low viscosity cases, because otherwise the linearization breaks down, and these first order perturbation assumptions are not correct anymore. So that's why we stop here, but we will be happy if any of you guys have an idea to how to solve these equations and want to collaborate. But in the next part, we came up with the idea and question that what would happen if we use higher molar masses. And these questions are generated by two other publications, because so far we had a very round story and we wanted to publish that, but just few weeks before our final draft, two papers were published from two independent groups, one in Netherlands around Professor Snoyer, and one in Sweden around Professor Amberg, that both groups are working on the water and PEO solutions, and both claim that adding the polymer is not changing the contact line motion. So they claim that the drop spreading of polymer solution that they have is very similar to the water case, which was very surprising for us at the beginning. So that's why we dig into these two papers. There are few remarks on these papers. First, that they are using higher molar masses compared to what we use so far. So they are using 4 million gram per mole. And the polymer relaxation time in their cases is huge, something like a 20 milliseconds. But the experimental timescale that they use is the inertial capillary timescale, which knows about the droplet size. And in their case, it's 3 milliseconds. Comparing these two timescales reminded us that in polymer physics, it's known theoretically that when you start to shear a sample, it takes some time for the sample to reach a steady state. And it was known, but for not PO, but for another polymer, Philossopoulos group in Greece showed that when you start the shear, the samples is behaving differently compared to the steady state. And all the rheometers that we are using are giving us these steady state values, but we don't know what happens before that. So, and also from the polymer physics, we know that these polymers can contribute to the viscosity when we gave them enough times. So with having these pieces in mind, we prepared two different sets of the samples with higher molar masses. One is 1 million and one is 8 million. And then we take a look at the drop spreading of these samples. I took one examples here, which illustrates what I want to say. But when we are looking at the spreading of these polymers, we find out that there is an additional regime popping up. So so far we had this inertia dominated and viscous dominated regime, but it seems that in the polymer in high molar masses, we have another regime popping up, which lasts for something like 2 milliseconds. But surprisingly, it follows a square root of the time, which means that in this time scale, the polymer does not have enough time to contribute to the viscosity. And then if we wait enough, then we will get another spreading curve. And then when we compare these results, we are at the first, we are in half. The exponent is half, and then it drops to 1/3. So our hypothesis is that below these time scales, which is in this case is 2 milliseconds, but what they reported is 3 milliseconds, but it's very close to each other. The sample that we have is somehow purely elastic, not viscoelastic. To show that, we use a non-dimensional number, which is called elastocapillary number. And the elastocapillary number is basically the ratio between the polymer time scale, so internal time scale of the sample that we have, divided by viscous time scale, which is the experimental time scale that we have. So, and then when we write it down, it will collect the polymer relaxation time, surface tension, viscosity, and the characteristic length. In this case is the drop size that we choose. And when we plot the exponent versus the elastocapillary number, a very nice observation is made. And that's that by increasing the elastocapillary number, we are decreasing the exponent, but only up to around elastocapillary equals to unity, which means the internal and external time scale are balanced with each other. After that, there will be a rapid increase in the exponent by increasing the elastocapillary number, and then we are reaching something like a plateau. And then it's regardless of the hydrophobicity of the substrates. Yeah, in this case, it's hydrophilic, but if we do that on a hydrophobic substrate below 90 degree, around 90 degree, we see also the same behavior, but it's a little bit shifted because of the changing the value. But the physics behind that is much deeper, and then it just shows this ratio between the time scale of the experiment and time scale of sample that we have is crucial. And then for these two publications that I mentioned, they are we couldn't directly measure the elastocapillary for their cases because we don't have access to their data, the entire data set. So, but roughly when we are calculating, these two publications are in this range. So they are in this plateau region that elasticity is dominated. So by that, I would like to conclude the first part of my talk. And that's we show that the drop spreading is the startup of the shear. So it's a very high shear rate process. It's transient. And in these high shear rate and transient situation, the time scale of the experiment matters. And if it's not matching the time scale of sample that we have, we might observe something which is not the entire story. What I explained so far and much more are collected in this paper, which is recently published on JFM. And if you want, you can take a look at that and then ask me a question or write me an email regarding this part. The second part is the coalescence of viscoelastic drop on a solid substrate that we are looking at. Sorry. For that, if we recall our example of application, this inkjet printing, these drops are spreading over the surface and then they merge to each other. So this is somehow the second part of this story about the applications. But it was not the only motivation to take a look at that. The other motivation that we had was from the hydrodynamics, because in drop dynamics, repeatedly the scientists claim that you can compare drop spreading and drop merging. Why? Because when you have a drop merging in the connecting bridge between two drops, a mirror plane forms, which has which no liquid is going through that. And then they said that it can act like a solid wall. So then you can compare the drop spreading to drop merging. Personally, I don't believe in that because here you have a free stress boundary condition in the glass substrate or solid substrate. You have a solid boundary condition, solid substrate boundary condition. But at the end of the day, this comparison worked to some extent, and it's somehow repeatedly reported in different papers. So we wanted to look whether it's the case for our samples as well or not. So I will start with I would call that a very fun experiment that we are looking at drop spreading from the side. The first one is just the water and water, so two water droplets. And then when we are looking at the connecting point of these two drops, it's fluctuating a lot. So if we measure the height of this connecting point, then we will get a very wavy equation, wavy data, which is because of the capillary wave, which is acting on the water cases that we have. But if we are increasing the viscosity and looking at the two glycerine droplets, we will see that the height of connecting bridge between two drops are just increasing monotonically. And then that's a very well-known feature of these capillary waves. So if you are looking at the water case and then adding a little bit of glycerin more and more, we will kill the capillary wave. And then all of these waves can be fitted by decaying sine function. And then in the Newtonian world, when we are increasing the viscosity, we are decreasing the damping time scale. So, but what would happen if we have water and PEO with 8 million PEO inside? For reference, the zero shear rate is 2.5 times more than pure glycerine. So we are expecting nothing happens. But when we look at the connecting bridge between these two, we will see that it's not fluctuating as much as water because still it's more viscous, but it's not as steady as glycerine as well. So it's going up and down. And then when we are looking at the curves for this intermediate size, 300 kilogram per mole and 600 kilogram per mole, they are behaving like Newtonian. So by increasing the viscosity, the zero shear rate viscosity, we are killing the capillary wave inside. But for very high molar masses, these capillary waves reappears again. And in this case, this relation doesn't hold anymore. So by increasing the zero shear rate viscosity, we are not changing the capillary damping time scale. Actually, the damping time scale of these two samples are very close to each other, although the viscosity is 1 order of magnitude different. So, but I'm not going into the details. We are in the process of submitting a paper on this. So if you are following our publication record, you will find out more about them. But let's come back to what would happen if we measure this age versus time, and then fit a power law curve onto that, and then extract the exponent. How does it work? How does it behave versus elastocapillary number? And when we are looking at that, the behavior is quite similar. So by increasing the elastocapillary number, we are decreasing the exponent, and around 1 we reach a minimum, and then a rapid increase and reaching a plateau. But there is one remark that the absolute numbers are not the same. So there is a connection between drop spreading and drop coalescence, but they are not identical. And that's again something that we discussed in that paper, which will be soon published. By that, I would like to conclude my talk. So this early stage of drop dynamics, no matter it's a drop spreading or drop merging, both are a startup of the shear. So the time scale of the experiment matters to see the effect of different behavior of the polymers into the dynamics or not. Drop coalescence and spreading have similarities, but also have are different. And also the elastocapillary number is a good parameter which connecting the internal time scale of sample that we have to the external wetting time scale. And then by that, I would go to the next steps. Now, I addressed the link between the polymer science and wetting, but we need to go to granular suspension. We did some experiments on that. Also looking into the complexer geometries might have some added values for the fundamental point of view. And then by that, on these granular suspensions, I have 2 short slides. It's on one of our PhD students' work, Reza, who did a very nice job. to connecting the rheology to flow field of the samples that he has. I'm not going into the detail, but he has he developed a series of different samples, transparent samples, and also he has astigmatism set up to take a look to the flow field inside the liquid. So by this defocused particle velocimetry, he can find the flow field inside the droplet, and then we can connect these results to the rheology. So comparing that to the traditional rheometers, we don't know anything about the sample itself inside. We just get the results from the device. But with what Reza is doing, it's opening up a new vision to see, to interconnect the wetting to rheology. And then by that, I would like to thank our collaborator. I just mentioned few names. There are much more people who are helping me, and I'm thankful. And also SFV 1194 for the financial support. And thank you for attention, and the floor is open for questions. Thank you very much.
Thank you, Peyman. Thank you so much.
Yeah, thank you. It was a very nice talk. I don't know if you can hear me.
Yeah, I can.
A bit low, but yes.
Okay.
I
Is
mean,
there
at
any
least for me.
question in the audience already?
Okay, perfect.
Because I had some questions.
Yeah, sure.
Okay, so this is very funny. I'm dealing with some capillary bridges in my thesis, and
Yeah.
I have some contact line and dynamics of that, of course. And I wanted to know, like, if you were looking at the contact angle versus the contact line velocity, and if you were finding the same quasi-static, those law in power 1/3, or if you were digging into that or not at all.
Yeah, sure. The reason that we look into the contact line velocity and contact line position was that because it was more straightforward. But we are also, if we are looking at the contact angles versus the time, we will find the difference easily between the polymer solution and Newtonian liquid. So yeah, sure.
It's the same models that you can find.
Yeah.
Yeah.
It's in the same direction. Let me put it like this, because contact line is more, I guess it's more sensitive compared to the contact angle, but it's in the same direction.
Okay. And because also you mentioned that at the contact line, you have eventually some viscous dissipation.
Yep.
And you were saying that your contact line is going at 1 meter per second.
Yep.
And
it is spreading, so it's going in the other direction.
That direction, sorry.
Yeah.
It's doing that direction in my setup, sorry. And so it's doing like that. And on what scale does it spread? Because I guess the deep dissipation, you have it because of the size of the spreading, and the velocity, the viscosity, and I guess the thickness also of the film.
Yeah, exactly. That meter per, because we were interested into something like the first 20 milliseconds or so. So there, it's a very rapid spreading. But if we look at the process for a longer time, so the velocity drops down, so the shear drops down as well. But in the earliest stage, it's starting from above 1 meter per second and then going down and down. But for example, I know that for drop breakup or rupture, it's a opposite direction. So close to the breakup, you are diverging the velocity field. So
yeah, exactly. And you have not measured those, no? Like quantify more or less, because it's super difficult, for example, to get the thickness of the film and so on. Like you need,
Yeah.
I don't know if you have tried to look from the bottom of
from
the
the bottom.
Yeah.
From the I would say that in this case it's not have any added value for us to take a look, but we have a
Yeah.
collaboration with Professor Hart, and I guess that the paper is available on arXiv, that we are looking at the breakup of the drop on the surface.
Okay.
And there we developed a model to measure the thickness of the film and also the curvature and the
Wow.
contact angle. So that
Because
would
that
be
is super difficult to do.
yeah. Yeah,
Okay.
we had a very long discussion with them
Yeah.
to find out. But we did that for just Newtonian liquids. But
Okay.
if you're interested, we can have another meeting sometime, and then we will
Okay.
discuss with the student there
And
as
that
well.
becomes a bit personal. But
Yeah.
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 Is there anyone that has question? Because that is super interesting. Because
Cannot
I
see
had
the
also
chat. Okay, because
no, I cannot see in the chat
okay.
either.
No, I
Okay.
didn't see any.
Okay. Yeah, please.
It's not really a question. It's just I really liked the movies with the 2 drops of water or glycerine. And do you have an explanation why the time for the polymer mixture is I mean why is it so
Capillary wave.
different? Yeah, why is it so different?
Yeah, that's exactly because for these very high molar masses, the polymer solution that we have are acting to some extent, acting like an elastic body. So it's somehow a non-viscous at the beginning, and then when we are, because if I go in the backup slides, if we are looking at the time relaxation time scale of these 2 samples, it's in order of seconds. And then what I showed here is in order of few tens of milliseconds. And then to this point, the polymer is not relaxed and not contributing to the viscosity. So it's close to the non-viscid case. So that's why we are questioning this part, because the viscosity in these cases cannot be the correct fitting parameter for the capillary wave. And what the elastocapillary number is, because I also have that in the backup slide. Yeah, if you are looking at the damping time scale, again, we see this more or less the same dependency to elastocapillary number. And that those 2 samples that I showed are these one, and they are very close to water case or a little bit water and glycerin.
Very nice. Thank you. Thank you.
Just a technical question.
Yeah, sure.
Can you go back on the video of the drop that does pew?
Yeah.
That spread on the surface? There was like maybe it's just an artifact, and it has nothing to do with the fact that you have put some PO in it. But on the left one, you can see a line. Is it like you see on the left video, there is a gradient, a gray thing that is going down, and there is a line. Is it a reflection of something?
Here? Yeah, it's
No,
just
in the center of the drop. Yeah, it's just a reflection.
Yeah, it's just a reflection. So
Okay.
let me play that again. You mean which line? This line?
No, the middle of the drop, the physical drop.
This one. It's just a reflection of the
It's also a
glasses
reflection.
slide from the
Okay.
behind of that. Yeah.
Okay, that was just a
this one.
question in case there
Yeah.
was something else.
Yeah,
And there was some polymer flowing.
No.
I'm not doing what.
No.
Because I'm not used to work with PO, with glycerol a bit more, and also at those percentage, I guess you had some hygroscopic effects a bit. You need to control the humidity
yeah.
and so on. It's a bit
Yeah.
difficult.
We
But thank
did the
you very much
experiments
for
in
this.
a well-controlled lab, so
Thank you very much. I know it's a bit difficult. Thank you. So I guess with that, anyone can ask any question by email and so on.
Yeah, sure.
I guess we can thank you again for your presentation. It was very nice. I
Thank you
really
so much. It
enjoyed
was
it.
very
Thank you
great.
very
Yeah.
much. Thank you.
Yeah, thank you.
Michelle, maybe if you want to
You
share the
can
last
stop
thing.
recording here, maybe.
Yeah. Bye, YouTube.